Hello and welcome to another video. In this video we're going to be working on find the maximum sum of node values. And in this one you have an undirected tree with n nodes, and so just if you didn't know, whenever you have a tree with n nodes you're always going to have n minus 1 edges. So if we actually look at, or I guess I don't have the constraints, I think the constraint is like 10 to the 5th nodes, but you'll basically, if you have 3 nodes you'll have 2 edges and so on, because that's going to make a tree. If you add any, notice if you have n minus 1 edges, the tree will be connected, and if you add any, if you can't add one more edge without making a cycle. So like there's nothing you can add here to not make a cycle. So whenever you read tree, you're always gonna have n nodes and n minus 1 edges. Okay, so there's an edge between ui and vi, and there's a positive integer k, and an array of integer numbers. So this is a little bit weird, but essentially every node has a value, so I don't know why they did this. I mean, I guess just to symbolize the edges, but essentially every node has a value, and you can perform the operation as many times as you want. So you can take an edge, and you can take both of the node's values, so this value and this value, and you can XOR it with a k value, and you can get new values. And then you want to return the sum of all the node values, the maximize sum. So you can do this operation as many times as you want. You can do it on the same edge as many times as you want, and on any edges. And so if you do this, so essentially here the values are 1, 2, 1. So basically what you're going to want to do is you're going to want to take this edge and XOR with k, which is 3, and you will get 2 and 2, and then you'll get a sum of 6. In example 2, so here you have a 2 and a 3, and you want to do an XOR as well. So if you take this edge and XOR with 7, I think you get 5 here, and you get like 4 or something here. So you'll get 9 total. And then here, all these values are 7 and k is 3, so if you do an XOR, the values will just decrease, so you just don't do anything, and then you'll get a total of 42. So instead of doing like a traditional way of solving this problem, this is a good problem to like help building your intuition. So you could do, I think you could do like DP or something, but the intuition used for this problem isn't some crazy thing that like you can't come up with if you only if you've seen this problem. And so we're gonna look at some observations, and then from those observations we'll build a pretty intuitive solution. And I think it is kind of a nice problem because it's not just like, did you memorize DP or something? It's like, can you see something, spot a, I mean, it's not that hard, but something, you know, like a pattern, and use that pattern to solve the problem. So let's say we have a tree here, and we have a k value, and it's just an arbitrary k value, and the nodes have some values. So let's say every node has a value. So if we take an edge like this, and we just say, okay, let's do this operation where we take the node's value and XOR it with k. Basically what would happen is, I'm not going to do the v XOR k, I'm just going to say, if I put a k here, that means k will be XORed with the node's value. So essentially with this edge, k will be XORed with this node's value, and k will be XORed with this node's value. And then if I have like multiple things, that means you just XOR them all together. So now let's take a look what happens if we take this edge as well. Now if we take this edge as well, this node's value, which was, you know, v XOR k, will now get XORed with k again. And so something that you can notice is k XOR k is 0, right? A number XORed with itself is 0. A number XORed with itself an even amount of times is 0. It's because all XOR is doing is counting how many 1 bits are in a certain location and how many 0 bits are in a certain location. So if a number is XORed with itself, no matter what it is, it'll either have 2 1s or 2 0s, which both XOR to 0. So essentially, if I perform this operation like this, then what's going to happen is this number, this value will get XORed with k twice, and then this will get XORed with k. So what will happen is this kind of cancels, and now this value stays what it originally was, and these two values become the value XOR k. So from this, you can deduce that I can actually build a path from any 2 nodes. So let me delete all this. From any 2 nodes, where I will just change those 2 nodes' values, because if I keep doing this, look, let's add another route, right? So we have this. So with this was XORed with k, this was XORed with k, and this was XORed with k twice. So it just canceled out. Now if we keep adding to our path, then this will get XORed with k, and this will get XORed with k again, which means it cancels again, right? So you can say like, if I have a path from node x to node y, only those two values will change. So those two values will become x XOR k and y XOR k, right? Like I can keep building this path, and you can do this with any two nodes. So it doesn't really matter which two nodes you use here. Like I can take this node and like build this whole path like this. And then what will happen is this node will get XORed with k, and this node will get XORed with k. And all of these will get XORed with k twice, because there's two edges here. So you can basically build, and in a tree, right, the whole concept of a tree is every node is connected. So you can build a path from any node to any other node and change those two values. And so from doing that, you should figure out, like, what does that mean? And what it means is I can take two nodes and XOR, and I can do x XOR k and y XOR k as a pair, right? So you don't actually need to know like what edges. You just need to know that like when I do this operation, I have to do it in pairs. So then let's go back to that question now. So let's just say we have an array of a bunch of numbers, right? And now our problem is basically, let's just say our numbers are like this, like literally this. And let's say k is like something, I don't know. Let's say it's 4. So now basically you can say, okay, so I can take any two nodes as a pair and do this operation. So obviously if I can find pairs of nodes that I can increase both of them, it doesn't really matter which order the pair goes in, right? Like if I take this pair and this pair, if I do that, then all of these nodes get XORed with k. Or if I take this pair and this pair, then all of these nodes get XORed with k. It doesn't really matter. It just means if I have an even number, I have to have an even number of nodes to do this operation. Because anytime I do this operation, I will change 2. So essentially, then what you're going to say is you're going to say, okay, well, what if I just take every node that when I XOR with k gives me a bigger number? So let me find those. Like this gives me a bigger number. Maybe we'll have a little check mark. This gives me a bigger number. This gives me a bigger number. This gives me the same number. And then 5 would give you less. 6 would give you less. 7 would give you less. 8 would give you more, I believe. 9 would give you more. We'll double check these, and these. I think these will give you more if you XOR them with k. We'll double check those. Because 4 XOR with k gives you the same thing, right? So 4 XOR with 4 will give you 0. 5 XORed with 4 will give you 1. 6 XORed with 4 will give you 2. This will give you 3. So these will give you a smaller value, and these will give you a bigger value. And we have an even amount. So you'll basically run into two scenarios here. Scenario 1, even amount of nodes want this operation. Then I know I can just take any pair of nodes here, doesn't matter which one, and make a path. Like for example, let's say node 8 and node 9 happen to be here and here. I can just say like, okay, well let me just go through the path for that and let me perform my operation on that path. And when I do that, then these two nodes will change and everything else will be the same. And you can do that for any two nodes in the tree. We already proved that, right? Because the whole tree is connected. So if we have an even number, we can basically just say, okay, perform on all. And let's just double check that this was correct, right? So for example, like 1 XOR 4 would give you this. So we'd get 5. So that's correct. 2 XOR 4 should give you 6. So this will give you 5. This will give you 6. This will give you 7, I believe. So 8 looks like this. XOR 4 would give you 12. I think. So if I did the XOR wrong, it's fine. It doesn't really matter. So this will give you 13. This will give you 14, I believe, hopefully. Okay, so essentially, okay, let me just change all these values to their bigger value, and let me take a sum. So I can just take this sum, and this sum, and that's fine. Like it's a pretty easy. You just go through your array, and then for every single number, first you count up like how many you have, and then if you have an even, you can just do the operation. But what if I have odd? So if you have an odd, you kind of have two scenarios, and you have to pick one. So let's actually go back to this. Like let's say we have one more number that we want to increase. So let's just change one of these, right? Let's change this to a 1. Well, now we have an odd amount, and we know that when we do this operation, we change two numbers. So there's no way we can, so this 1 XOR with 4 will give us a 5. So there's no way we can do it on all of these, like if we just take only these numbers. So there's kind of two things we can do. And this will always, you'll basically branch in two directions. Direction A is I can be like, okay, well, I have an odd amount. What if I just do all the ones that give me the biggest increase and then not do the other one? So for example, this is an increase of 4, 4, 4, 4. I guess these are all the same. It's not always going to be the case that it's all the same. In fact, yeah, I'm not sure if I did this correct. Hopefully I did. But let's say this number, like let's just say some other number. I guess with 4 it wouldn't work, but let's say, for example, instead of 10 giving us 14, 10 happened to give us something else. So let's say 10, instead of gave us 14, would give us like 11. Let's delete this. So let's just say this gave us 11. And we'd be like, okay, well, everything else increases by 4, and this only increases by 1. So we'll just take these and not do the last one. So that's one thing you can do. Is you can say, like, okay, take every number and do XOR except for smallest one, right? So take every number that benefits from doing the XOR except for the smallest one. But there's another thing we can do. And another thing we can do is we can say, well, we can just take all of these, right? And what we can do is, yes, these get minimized, but by how much? Like for the extreme case, let's say this wasn't, let's say this got increased by a lot. So let's say it goes back to 1. So 1 would get increased to, gets increased to 5. And maybe like some number gets decreased, but it's not by that much. So actually with 4, they would all get decreased by 4. But let's say this number actually didn't get decreased by 4. Let's say it got decreased by like 2. Right? So we say like if we do this operation, it will get decreased by 2. Well, in that case, we can say like, okay, well, we need an even amount. So we can take all of these, and then we can also do this. And this is beneficial because every single one of our increased numbers gets increased by more than our smallest decrease. So essentially your second path is keep track of smallest increase and smallest decrease and add in smallest decrease to make number even. Right? Because if we have an odd number of nodes that we know we want to increase, we can just say like, okay, well, we'll just add one more. That's a decrease, but it's small, so it's still worth doing. So basically, you just keep track of like these two things, and then you just say like, well, what's the smallest increase and what's the smallest decrease? And if the smallest increase is bigger, right? So smallest increase is bigger than smallest decrease, then we would want to take this pair, because we'd basically like, this would be maybe like 5 and this would be like 3. So we'd get a total sum gain. So that's kind of the whole problem. Step 1, realize I can make a path for any 2 nodes, and then that would just change only those 2 nodes' values. And that's pretty reasonable. Like there's a lot of problems that are like the total path from one node to the other node is like b minus a for each edge, where b is the node you go to. So you realize like, okay, if it's b minus a and then b minus a and then b minus a, then really the total path isn't that. It's just going to be like the last value minus the first value. So same kind of thing here. In a tree, we can connect this and we can make a bunch of paths. So like we can make this path, and we can use this operation as much as we want. So we can make this path to change these two. We can then make another path that even intersects here. So we can say like, maybe we'll take a path like this to change these two as well, and so on and so on and so on. So hopefully that makes sense now that you know, like once you realize the pathing, it's basically just given an array of numbers, you can do this XOR operation on a pair, and then what would be like the biggest result you can get. And the biggest result is just do it on everything that increases, check for even. If it's even, you're done. If it's odd, then figure out, do I want the last number and a decrease, or do I just get rid of the last number? And that's essentially it. So hopefully that makes sense, and now we can code it. So we don't even care about our edges. We're not going to be using them at all because we know the tree's connected. So we're just going to go through our nums and actually just keep track of like how many nums do we have that we increase, and what's the smallest decrease. And that's basically it. So let's do that. And also a number can't go, maybe if k is 0, but I don't think k can be 0. So a number XOR with k can't be itself, because the only time a number XOR with k is itself is if you XOR with 0. Okay, so we'll have like total nums. We'll have like a sum or something, or result. We'll have smallest decrease. And then we'll have smallest increase. Okay. So now let's go through all our numbers. So for int num in nums. Like I said, we don't really care about the edges. So basically the first step is we're going to check, is this operation good to do? So if num XOR k is greater than num, then this is good to do, right? Into Boolean. So I think we need to do this. Let's see. So k is not a Boolean. That's weird. Okay, it just took a while to update. Okay, so if this is greater than num, then we want to keep this as a number that we're going to be increasing. So we're going to say total nums plus plus, and then this is the sum we're going to, this is the thing we're going to add to our actual result. So we'll say result plus equals num XOR k. Also confusing by this. Okay. Oh yeah, we have to initialize these. So because smallest decrease, we're trying to minimize both of these. We can just make them like infinity or something. So I think there's like an integer max int, something like that, max value. So we can just initialize it both of those. Okay. So now, yeah, now that should be fine. So we increase our total nums, we increase our result, and we want to keep track, is this the smallest decrease? So we can say smallest, or sorry, not decrease, increase equals max of smallest increase and this current number. Okay. Otherwise, so remember, it can't be the same, so otherwise it's going to be a decrease. So we kind of do we do the other stuff. So in this case, we're not going to want to mod it. We're not going to want to XOR with k, so we'll just keep it the way it is. So we'll say result plus equals just the number, because this is going to be a decrease. But we do want to see, is the decrease, like we want to keep track of the smallest decrease, so that would go here. Decrease. Right. And then, yeah, so this is all the same. Oh, sorry, these two need to be min. Okay. So that's basically it. That's going to give us a sum, and it's going to give us how many numbers we've used. How many numbers did we use to change, right? So total nums is the numbers we perform this operation on. So if total nums mod 2 equals 0, if it's even, we're done. So we can just return result. Otherwise, we kind of have two branches, right? One branch, get rid of the smallest increase. So we can say return the maximum of result minus smallest increase. So that will just make it even. Or result plus smallest decrease. Might have an issue here. So I think I did a little bit something wrong here. Yeah, so this needs to be not this. This needs to be num XOR k, and then this needs to be minus num. And now this needs to be the other way, like this, because we need to actually keep track of like what's the increase and what's the decrease. Yeah, and then also this needs to be a minus, right? Because it's a decrease. So this will be positive. Yeah, this will be a positive number because this is like, this will be bigger. This will be a positive number because this will be bigger. So I think this is fine. So we either get rid of our smallest increase or we add our smallest decrease. I think that's good now. Let's double check. Is it like a long or something? Yeah. So typically whenever you get a result that's like, let's see here. Yeah. So whenever you get a result that's like not the right, like a big number, it's usually just because it's a long, and that's what it is. So this needs to be a long. Maybe we have to change anything else. Let's see. Nope. Okay. So yeah, and this is one of those problems that's like, to do harder problems, it's not just going to be like, do you know DP? It's going to be like, can you make reasonable, you know, inferences from problems? Can you figure these things out that do require, you know, being like doing problems and finding these patterns? That's not just like, oh, just perform a DP or perform a BFS or perform a DFS. It's like, can you actually make some observations? Yeah, so this is going to be, time and space is going to be pretty simple because we just went through our numbers once. We didn't use our edges at all. So this is just like O, and I guess we have the nums. And space is O1 because we didn't use anything. Yeah, we just have like constant variables. And yeah, so it's going to be all for this problem. Hopefully you liked it. And yeah, definitely, if you didn't see this pattern, definitely, hopefully you can see these things in the future, that it's not some crazy thing. There are some problems that's like just some ridiculous thing that basically, if you haven't seen it, no way. But I think for this one, it's pretty reasonable to understand, like, and you are going to get a lot of problems. One more thing, I guess. You are going to get a lot of problems where you do get these random operations that you're allowed to do. And what I would say is, like, draw it out, do the operation in, like, a bunch of different ways, figure out what it's actually doing, and then figure out, like, is there, like, if I do this a lot in some way, does this, like, you know, does this simplify to something else? And that happens a lot. Like, this is a pretty common problem where they'll tell you, like, you can do some operation or 2 or 3, and you have to figure out, like, okay, if I do this operation like 1,000,000 times, can I simplify that, or do I actually have to do it 1,000,000 times? So yeah, hopefully it's helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.